article which is just put in the footnote to this slide. So let me start with brief introduction to the setting of Pole thought of the CCC. So let me. The story is as follows: that in this cosmological hypothesis, the universe consists of eons, each being a time-oriented spacetime, whose conformal compactifications have space-like scry. I recall you that scry is a hypersurface on which all the null geodesics end or start. So the universe consists of eons, each being a time-oriented spacetime whose conformal compactifications have space-like scries. So the Weyl tensor of the metric on each scry is 0. So what I should say now is what CCC is not. So CCC says nothing about this, what is the physics in a given eon when the physical age of the eon is normal. So what does it mean normal? Normal means that the eon is neither too young nor too old. So in the majority of the evolution of the eon, CCC says nothing about this. What CCC tells us, it tells us what is going on when an eon is either about to die or had just been born. In particular, CCC does not require that the eons have the same history. What this CCC is, it is conformal cyclic cosmology and not conformal periodic cosmology. So, for example, these conferences, these conferences here, these Lorentz geometry conferences are cyclic. They are every 2 years there is new conference, but these conferences are not periodic. Although at the beginning the conferences could look the same, at the end they could look the same, but during the conferences everything is different than in the previous one. So the CCC is cyclic cosmology, not periodic. So that's the main thing. So let's start over with the setting. So the universe consists of eons, each being a time-oriented space-time, whose conformal compactifications have space-like scry. The Weyl tensor of the form metric on its scry is 0. Eons are ordered, and the conformal compactifications of consecutive eons, say the past one and the present one, are glued together along scry plus of the past eon and scry minus of the present eon. The vicinity of the matching surface of the past and the present eons, this region Penrose calls bandage region for the two eons because the matching surface is singular for metrics. So this matching surface he calls wound. So the vicinity of the matching surface is equipped with the following three metrics, which are conformally flat at the wound. So all these three metrics are conformally flat at the matching surface. And the first metric, which is denoted by G, is everywhere regular in this bandage region. There is another metric, G check, which represents the physical metric of the present eon and which is singular at the wound. And ultimately, there is a Lorentzian metric G hat, which represents the physical metric of the past eon and which infinitely expands at the wound. So in the bandage region, the three metrics G, G check, and G hat are conformally related. So these three metrics are all conformal to each other. How to make this relation between these three metrics is debatable, but Penrose proposes that the metric G check and G hat are related by a single conformal factor omega. G check is omega squared times G, and G hat is 1 over omega squared times G, where omega vanishes at the wound. Now, the metric G check in the present eon is a physical metric there. Likewise, the metric G hat in the past eon is a physical metric there. And of course, the metrics J in the present eon and the metric G hat in the past eon as physical spacetime metrics should satisfy Einstein equations in their spacetimes, respectively. Okay, so the situation is like as follows. The picture which I drawn here is that this part from the red surface here down is the past eon. Everything which is above is the present eon. The thing which is here, like with wavy blue curve, this region here is this what Penrose called bandage region. So it is vicinity of the gluing of the past eon to the present eon. This bandage region is equipped with fully regular metric in G. And now in the past eon, there is a physical metric G hat, which is just the green one here, and in the present eon, there is metric G check. The metric G check and G hat is related to the metric G, this fully regular metric, by the function omega, which is singular at the which vanishes at the surface. So in particular, the metric G check at this surface is simply contracted to 0. On the other hand, this metric here just expands when approaching the wand. So that's the picture, and that's the mathematical objects that one can squeeze, and it was what Paul Todd squeezed from Roger Penrose's proposal. That actually what the really interesting physics and mathematics about this, what's going on with the past eon and with present eon, is described in this bandage region, and this bandage region is equipped with essentially with 3 metrics conformally related: G, G check, and G hat, with the properties. And there is this function omega also that vanishes at the wand, and the wand is supposed to be conformally flat. So the wire tensor of this metric and any metric of the 3 vanishes at this wand. Okay, so that's the setting. So now what I wanted to do, I would like to see how to make a model of Penrose's bandage region of 2 eons. So what one needs a function omega vanishing on some space-like hypersurface, and a regular Lorentzian metric G, such that if G check being omega squared times G satisfy Einstein equations with some physically reasonable energy momentum tensor, then G hat, which is 1 over the squared G, also satisfies Einstein equations with possibly different but still physically reasonable energy momentum tensor. Okay, so if you just think about this, this resembles something which was done by Brinkmann. Thomas Leisner mentioned this work of Brinkmann in his talk. So this question of matching 2 eons and looking at geometry of them is similar to a question posed and solved by Brinkmann in 1925. So he asked a question: when in conformal class of metrics there could be 2 non-isometric Einstein metrics. So Brinkmann asked this question, and in 4 dimensions he found all such metrics without any assumption of the signature. So in each signature he solved the problem. So here the problem is similar. It seems even simpler. The same function should lead to 2 conformally related but different solutions of Einstein equations, with a prescribed energy momentum tensor on the m hat, which is the past eon, and a reasonable energy momentum tensor on the other side, which is m check. So if one thinks about this, it seems to be very unlikely that one finds something interesting on this m check, meaning on the present eon, when the energy momentum tensor and the metric in the past eon is given. So I simply wanted to check what's going on when each one starts with very simple examples about such things. So to get some intuitions, let us check what we can do in the conformally flat situation. Okay, and with such that one of the eons is equipped with perfect fluids. Okay, so to do this, let me start with some preparation. So it is just I will recall you something about Friedman, Lemaitre, Robertson, Walker metrics for simplicity, or for I just restrict to Friedman metrics or Robertson Walker metrics with spatial section being a sphere. So I start with the most general Friedman-Robertson Walker metric with the spatial section being a sphere. Here is the metric of this free sphere, right? And as perhaps you know from cosmology, it is convenient to introduce a conformal time, meaning you pull out the omega square in front of the metric, and you introduce the time, conformal time eta, which is related to this Friedman time t by this thing. And now what I try to recall you. So then if you do it like this, here what you have inside, when this omega square is pulled out, what you have inside is just like a product metric of time and a three-dimensional sphere. So this is the Einstein universe metric. So actually, if you just pull out this omega square, then you will write this metric G test, this Lorentzian metric G test, as omega square times Einstein spherical universe. So this parameterization in terms of eta rather than t is very convenient, since one can solve explicitly the Einstein equations for this G test with the right-hand side having energy momentum tensor of perfect fluid. So the perfect fluid here is just with the unit time like vector u, which is just this thing. And mu is energy density of the fluid, and P is a pressure, and I assume that the pressure of the fluid is just isotropic, right? And moreover, just if you just take this G test metric, so you have only one free function, this omega, and then if you put these equations, and moreover you assume that the perfect fluid satisfies the following equation of state, that pressure is proportional to energy density, with W proportionality thing being a constant, not a function. Then you can solve these equations. You can just put these Einstein equations on this function, and it turns out that you can solve it to the very end in terms of elementary functions, and the solution looks like this. So it is either a solution like this, where here the W is just this constant relating pressure to the energy density. So if it is not equal to -1/3, the solution looks like this in terms of elementary function. And if it is -1/3, it is just this, okay? So this is just recollection from Robertson-Walker cosmologies and perfect fluid. And now if I try to apply this G-test metric to build some stupid model of this Penrose's bandage region. So let's try to do it. So now we go back to the Penrose-Stotz bandage triple, G check, G, and G hat. So I take as G this metric, which is everywhere regular, the Einstein metric. So this metric, which is just Einstein universe metric. This one here. The Einstein universe metric will be just my G, and now I take as G check precisely this thing that I considered a second ago. So it will be just my metric G test, and then as G hat, I just apply this, which Penrose calls reciprocal hypothesis, how to get G hat from G check or G check from G hat, that the omega factors should be one over the other with minus sign. So now, since I assume that G check, this G test satisfies this perfect fluid equations with polytropic equation of state, then obviously G hat will also satisfy the same equations, because if I take 1 over omega 1 over this omega square, simply the 1 over 1 minus 3w goes to minus 1 of these. So then if the metric G check satisfies these polytropic equations of state, Einstein equations with perfect fluid, then G hat also satisfies this with merely W from this metric going to W hat related like this, or what is the same, that W hat is minus 2/3 of minus W. So as a consequence, if this guy satisfies these polytropic equations of state, Einstein equations, this guy as well, but these polytropic constants are changing, are related by a very simple relation. So what's going on here? We have the following very simple and stupid theorem. If omega is such that G hat satisfies Einstein equations without cosmological constant and with the energy momentum tensor T of a perfect fluid whose pressure is proportional to the energy density mu check via P check equal W check mu check with W check equal constant, then the metric G hat also satisfies Einstein equations with cosmological constant, but now with the energy momentum tensor of perfect fluid whose pressure is related again by polytropic equation of state with different constant W. So one should, it is still interesting to see what is the Ricci scalar of this metric, let's say G check, and you can see that this Ricci scalar is positive essentially everywhere, provided that this thing is greater than 0, that this thing 1 minus 3w greater than 0. If I want that my energy momentum tensor in the check region satisfies the dominant energy conditions, then it turns out that I have to restrict my W check to this value. So what and why I need Ricci positive? Because when Ricci is positive everywhere, meaning that Ricci is also positive at the wound, and this means that the wound is space-like, and that's what is needed in the proposal. Okay, so somehow the theorem says that I can just transmute by this reciprocal hypothesis of Penrose of changing omega to 1 over omega, one perfect fluid in the, let's say, past aeon or previous aeon to the another perfect fluid in the present aeon. Perfect fluid have the polytropic equations of states, but the polytrops constants are changing. So this story is as follows: that I have here. I made a conformally flat now this bandage region, in which the metric G is just Einstein static universe with spherical sections. The wound is conformally flat, of course, because the metric is conformally flat. The G check metric satisfies Einstein equations with energy momentum tensor of perfect fluid with polytropic equation of state with W check being constant, and this one satisfies the same kind of equations, but now with only things that W check is now replaced by W hat with this interesting sort of relations. So somehow you can think that having a perfect fluid with W hat here, this perfect fluid passes through this wound. By this reciprocal hypothesis, it starts to be again perfect fluid, but different one, because now W's are changing. Okay, so let me tell you a few words about these W's. So if in the if in the past aeon W is -1, if you just look at the perfect fluid energy momentum tensor, mu is equal minus P, when mu is equal minus p, so when w is equal -1, there's no this part. So actually this equation then is equation essentially Einstein equation with cosmological constant. So -1 w corresponds to cosmological constant type of solutions. So if we have, let's say, cosmological constant conformally flat solution at the end of the past eon, which is simply de Sitter space, then by this reciprocal hypothesis, it in the new eon, it has w check equal 1/3, and this perfect fluid corresponds to incoherent radiation, because it is like a lot of radiation. So somehow de Sitter at the end of the universe of the previous eon becomes radiation in the new eon. And then there are some other values here. For example, matter content of perfect fluid. When you have perfect fluid with simply pure dust, then this W is equal 0. So when W is equal 0, then we go to new W in the present eon equal to -2/3. These -2/3 polytropes are also known in cosmology. They are called gas of domain walls, whatever it means. So, for example, matter in the one of the eons gets transformed to gas of domain walls. Then there is another thing which is interesting point on this line here, or on this interval, is point corresponding to W equal -1/3, because -1/3 goes to -1/3. And these -1/3 polytropes are also known in cosmology as gas of strings. So somehow gas of strings, whatever it means, pass through the wand. Okay. So since this, so the most appealing is this case when de Sitter is transmuted to pure radiation. De Sitter at the end of the previous eon is just transmuted to radiation in the new eon. So let me look at this case more carefully, only in this case. So let me now start again the same story, still in conformally flat regime. So we come back to Robertson-Walker metric, but now in the usual time of Robertson-Walker. And again, I just pull out this omega, but now I will be working in terms of this t coordinate instead of this eta coordinate. So I just pulled out this, and of course this is the Einstein universe metric, this red thing here. And then now I want to show, in my previous example, I assumed that cosmological constant on both sides were 0. But now, and if there was cosmological constant, it was like coming from perfect fluid. But now I will assume that I will put the Einstein equations on this G-check metric, assuming that there is a cosmological constant. So I want that now my Einstein equations are just Einstein tensor plus cosmological constant lambda check times d check is equal to energy momentum tensor of perfect fluid with polytrope. So if I do this, I get that's how the differential equations for this function omega as a function of t looks like. But now I also want that G hat satisfies Einstein equations now with cosmological constants lambda hat and the same kind of energy momentum tensor, but now the polytrope is just p hat, w hat, and mu hat. So then, because there's the same omega on both things in G hat and G check, I will have similar equation, but now to -1 over omega. So this system is very stringent. Somehow I will be having twice second order ODE for this omega. So if I look at this integrability condition for these equations, it very quickly becomes something like this: that this is only possible that G check and G hat have perfect fluids of polytrope type with constant W check and W hat if the constants are related by this funny equation. So in particular, so these necessary conditions for this omega having a solution, we know the exact solutions when both lambdas are 0, but from these integrability conditions, you can see that actually both at least one of lambdas must be 0, or W must be equal -1, which corresponds to cosmological constant again, so it is not interesting, or W is equal 1/3, which is perfect fluid of radiation. So that's what you can get from very quick analysis of this double second order ODE for function omega. So if I just concentrate on this case when, so the integrability conditions, I said that there is this 4 possibilities in particular, but in particular, if I just restrict myself to the case when lambdas are non-zero and W check is equal 1/3, then it turns out that actually W hat must be equal 1/3. If you just go back to the equations, so somehow the perfect fluid, if there is non-negative lambda on both sides, the radiation goes to radiation on the other side, as it should be. And then one can just calculate explicitly what is this function omega in this case, and you can just integrate it to the very end. Both lambdas are appearing in this solution, and this function has the property that G check and G hat satisfy Einstein equations with polytropic perfect fluid equation of states, for which W check is equal W hat equal 1/3, which corresponds to radiation, and with the corresponding cosmological constants, which could be absolutely arbitrary. So the constants lambda here are lambda check and lambda hat are unrestricted in this solution. They should be non-zero, and if you assume that both of them are non-zero, and assume that you had radiation, let's say in the past eon, you will have radiation in the present eon. And his situation is quite different than when I assume that lambdas were both 0, because remember there 1/3 was going to -1, or -1 was going to 1/3. So somehow there is drastically different situation for when two cosmological constants are non-zero or where they are 0. So colloquially speaking, if there are cosmological constant, incoherent radiation passes happily through the wand. However, cosmological constant can change from any positive value to any other. Okay. So now let me pass to something more serious, and this is if you just look to Roger Penrose's proposal of CCC, which is perhaps the best described in his book Cycles of Time, then he says that if this proposal is true, there should be he can even give predictions of something that can be seen in the present eon from the past eon. He says that perhaps the first predictions that he can make is about this: what's going on when at the very end of the past eon, some very strong gravitational wave was produced by, for example, merging of two huge supermassive black holes. So if something like this happens, he says that the gravitational radiation, because it is null and everything is conformal here, should pass to the new eon, and it should be somehow visible on the cosmic microwave background radiation. So this is a picture from Roger Penrose. You say my pictures are very bad, so this is much more simpler version of this. So if there is some emission of a wave here, looking from the past, you should see somehow the intersection of this part of the future null cone of this gravitational wave there on the last scattering surface. And since last scattering surface is hypersurface, here you have a cone, so the intersection should be a sphere, which should be visible somehow. That's what Roger says. So if he says this, I wanted to make a very simple model where we have in the past eon only one spherical kind of wave, and I wanted to see what's going on with this spherical wave when this passes to the next eon by applying his reciprocity hypothesis. So let me tell briefly about this. So I now consider 2 consecutive eons. Sorry, can you hear me still? Hello?
Yes, we are here.
And you see everything what I show, right?
Yes.
Okay, thank you very much, because I'm paranoid. So I consider 2 consecutive eons, M hat and M check, from Penrose's Conformal Cyclic Cosmology, and study how the matter content of the past eon determines the matter content of the present eon by means of the reciprocity hypothesis. So I assume that the only matter content in the final stages of the past eon is a spherical wave described by Einstein equations with the pure radiation energy momentum tensor. So pure radiation energy momentum tensor is a tensor in which all the energy goes along null direction. So there is, and I assume that this null direction k is such that it is a propagation vector of a wave which has spherical front. Spherical in the sense that, for example, it has topology of a sphere. So I assume that in the past eon I have cosmological constant lambda hat, an energy momentum tensor of pure radiating wave. And now, of course, such solutions, if I want that this k will be just hypersurface orthogonal, then such solutions are well known. These are just they belong to Robinson-Trautmann class of solutions with cosmological constant. The problem is that if I take these solutions of Robinson-Trautmann, they are in coordinate system that doesn't fit to this setting of this space-like Scri plus. So somehow I would like to have these metrics as they satisfy these equations with these assumptions, but in terms in coordinates which are adapted to the vicinity of this wand. So instead, and the transformation, I think that there is no, it is impossible to make a reasonable transformation to make it visible. So I start the problem from scratch. So I solve these Einstein equations, associating to M the metric G hat as follows. So there is some metric, 3-dimensional metric, 1-parameter family of 3-dimensional metric HT, and I make out of this Lorentzian metric n divided by this. So this ansatz which I do is a Lorentzian analog of the Poincaré-Einstein metric known from the theory of conformal invariance. The solutions of this, what I want, is obtained under the assumption that the 3-dimensional conformal structure, which this HT, h of t equals 0 represents, is flat. I assume that the metric G hat admits power series expansion in the time variable t. So I mean actually that this metric HT, this 1-parameter family of 3-dimensional metrics HT, admits a power series expansion in the time variable t, and that H0 belongs to this, h of t equals 0 belongs to this conformal class. And it follows, so I assume that this conformal class is conformally flat. The 3-dimensional conformal class, which is base for this Poincaré-Einstein type of metric, is conformally flat. And now I just assume this, and it follows that such a solution depends on precisely one real arbitrary function of real variable r. So now I find this solution. I will pass to the details in a moment, but first I tell what I really did. So I get this solution, then I just take as my omega function equal minus t, and then I take the metric G hat, G check by this, and now I have nothing to do. The only thing I can check is what if this one satisfies this equation, what Einstein equation satisfy this metric. So if I just calculate the Einstein tensor and energy momentum tensor, then I will see that this region M check is filled at its initial state with 3 types of radiation, 3 types. At the beginning, in the previous eon, I had one radiation. There was this spherical wave propagating towards the end of the eon. But now, at the beginning of the next eon, I have 3 types of radiation. First, there is this damped spherical wave, as it was. So the spherical wave passes through the surface, but it is damped. And what happens at the surface, it turns out that you will see that there is another wave going in the opposite direction, meaning like a wave that is just like contracting, going. So there is another wave, which the ingoing spherical wave, obtained as a result of a collision of the wave from the past eon with this Big Bang hypersurface. And eventually, there is third kind of incoherent radiation of perfect fluid type with pressure equal to 1/3 of energy density. So the metric, if the metric G hat satisfies these equations on the previous slide, the metric G check satisfies Einstein equations with the following energy momentum tensor. There is pure radiation coming from the K vector as it was, but there is pure radiation of the ingoing wave, the contracting wave, and eventually there is perfect fluid like this. So that's the story. If I have a spherical wave in the past eon, in the new eon, this wave essentially propagates, but is damped, but it splits onto the wave that is just now focusing, and eventually some scattered radiation is produced. That's the result. So now the details. So I start with a conformal class of metrics. I put them in some coordinates. There is R coordinates real greater than 0 and Z bar. So that's my 3-dimensional flat metric. And now I make Poincaré ansatz for this 1-parameter family of 3-dimensional metric HT like this. So this an ansatz. So I say that there is some function mu of TR here and mu of TR here, and they are such that mu of T equals 0 and mu of T equals 0 is 0. So this precisely satisfies that H of T0 is precisely my conformally flat metric. And now I assume that there is power series expansion in T for this function nu and mu. And now I want to put the Einstein equations on this. So I take the Poincaré type metric G hat, which in this full beauty looks like this with this power series in T. And coordinates here are T greater than 0, R greater than 0, and Z being complex number. And now I consider the following null vector. So it is tangent to a congruence of null geodesics without shear and without twist, which represents light rays emanating from the source at the R equals 0 in the past eon. I require that the Poincaré type metric, that this one metric satisfies these Einstein equations with cosmological constant and with this vector K as a propagation vector. And now I can solve this. So let me write the theorem. If the metric satisfies Einstein equations like this with this null vector, then we have the following. First of all, the first 2 coefficients in the expansion, this A1 and A2 and B1 and B2 must be 0, and the power series expansions starts from T cubed. Then the metric G hat, or what is the same, the power series expansions of nu and mu, are totally determined up to infinite order by an arbitrary differentiable function f. So if you give me differentiable function f of r, then these guys are determined up to infinite order by Einstein equations. So more precisely, the Einstein equations for this pure radiation that I had on the previous slide solved up to order k together with an with a choice of arbitrary differentiable function f of r, uniquely determines nu and mu up to order k plus 2. So in the lowest order, the solution looks like this: nu is like that, mu is like that. The energy function of the cosmological and the cosmological constant are like this. So the energy depends. The leading term is t to the power 6, and it depends on f prime, where prime is just the derivative of f with respect to r. The cosmological constant up to very high order, actually up to infinite order, is constant. The y tensor of the solution is non-vanishing, but it vanishes as it should on t equals 0 surface. Okay. With the use of computers, I just want to show you how this solution looks. It's horrible, but it's you can handle it. So I just solve this up to order k equal 10. The formulas are still compact enough to show how do they look till the order 8. So the nu looks like this, mu looks like this, and the energy density, the leading term is, as I said, t to the power 6. So I have no patience to type the y tensor components up to high order, but up to fourth order I can still write them down. So there is some constant tensor Cijk al with properties of while, and everything is proportional to one function up to fourth order. Then some other components appear, but anyhow, y tensor at t equals 0 surface vanishes as it should in the proposal of Penrose. And of course, because I want the positive energy density, f prime must be greater than 0. So now I have no choice. So that's the summary. The Poincare type metric G hat can be interpreted as the ending stage of the evolution of the past aeon in Penrose CCC. The aeon has a positive cosmological constant, which is filled with a spherically symmetric pure radiation moving along the null congruence generated by the vector field K. Okay, so now let's apply the reciprocity hypothesis. Take as omega minus t, and then we will get the metric G check being like this with the solution given by previous theorem. So if this metric is taken from this news satisfying the Einstein equations of the previous theorem, then this metric satisfies Einstein equations like this, with K being as it was, but there is L appearing and this thing. And here K and L are the null one forms corresponding to the pair of outgoing, which is old K wave, and ingoing null vector. So there is +1, that's the one that we had, and there is minus, which is just like going back. And here the one form U is a vector field and corresponds to the future-oriented time-like unique vector, which is given by minus t to the minus 1 dt. So remember that in my past aeon, time was going from 0 to positive value of t. So in my present eon, my time is going up from 0 to negative values of t. So for example, now we have t smaller than 0 in the present eon. So for the solutions of the past aeon equations, we have the following, that the energy. So you remember that there are now two waves. There is the damped wave before with energy density phi check, and the focusing wave with energy density psi check. And now if you just look what's happened to the wave coming from the previous aeon, it's essentially up to the leading term. It just gets split onto two equal waves. Not up to every term, but the leading term is simply, the leading term is divided by half. Half of the wave passes and goes happily as it was going, but now the other half is focusing. So that's the first thing. You may say, okay, so now you see t is negative now, so there is negative here and this power free, so this is positive. So for positivity of energy of this entire model, not only I have f prime I only have to have that f prime is greater than 0, but also f should be greater than 0. Okay, so that's what you see from the formulae for the energy density of these coherent waves. But but moreover, you have still perfect fluid with energy density rho check and p check. But if you just look how rho check and p check is related to each other up to the leading terms, p is equal rho is equal 1/3 of p. So again, the leading terms here is just incoherent radiation. Okay. So that's so I'm concluding. Note that since in M the time is M check time is smaller than 0, the requirement that the energy density are positive near the Big Bang hypersurface implies that F must be greater than 0 in addition to F prime. Note also that these are the only conditions needed for the positivity of energy densities, as the leading term rho and rho check has force power. So here there is no problem. Remarkably, as I already noticed, the leading terms in rho check, p check, the terms with negative powers in T are proportional to each other with the numerical factor 3. So we have that close to the bank surface, this perfect fluid is just radiation. This means that immediately after the bank, apart from the matter content of the two spherical ingoing and outgoing waves in the new aeon, there is also a scattered radiation there described by the perfect fluid with P equal 1/3 of rho. This solution to the three metrics in Penrose-Stotz bandage region has the following appealing physical property. Immediately after the bank, the spherical wave from the previous aeon not only produces two spherical waves, one of which is obvious. It is the still expanding but damped wave that survived the bank. The other is less obvious because although it is still spherical, it focuses. And then there is third ingredient. There is the new aeon is filled with randomly scattered radiation described by the perfect fluid. So what the Penrose-Stotz scenario does to the new aeon out of a single spherical wave in the past aeon is that it splits this wave into three portions of radiation, the two spherical waves, and in addition, a lump of scattered radiation described by the statistical physics. Okay, so that's essentially the end of my talk. Here are some references. I love this paper of Brinkman, so I always quote it. The formulation of this, the base for my talk, the formulation, mathematical formulation, is in this paper of Paul Todd. There are two papers of one Krzysiek Meissner with me and one of myself. This last paper is just about this last model that I was just describing now. Thank you very much.